are logging in, the moderator is logging into the conference call so that we can ask questions as well. This is good. I'm glad we have this technology, because otherwise, terrible things. 45 minutes. That's the goal.
If you don't make it, what do you want me to do? You want me to cut you off?
What I want you to do is stand up and say, "Thank you, ladies and gentlemen, please leave."
So I'm going to go get
Okay,
code.
very good.
I'll be right back.
All right,
45 minutes, I'll say. That was brilliant. You're done.
good. That's what I need you to do.
I can go like this.
5. That would be brilliant. That would be great. That would be great. Theoretically, I ought to know time.
You count the slides, right?
I did. And I'm prepared to skip over some other slides. So, excellent. I can read the crowd. I can already see that this crowd understands this, so I'm going to skip over the first half. We'll be out of here in no time. So the remote people can hear me. I have gotten texts from them, which is excellent. We are not part of the conference call yet, but they can see and hear me, so I could get started, potentially. Lynn will be jumping in here and putting us on the conference call, but that would just be a little more divided attention.
Yes, okay, which is the topic today. We're all very proud that James, actually known as Zephy McKanna, is defending his PhD dissertation today. And welcome the family, friends, and all the supporters, and the cookies, too. Zephy has been with us. Misha Pavel and I knew him when he first came to Portland and was helping on a variety of projects, from all kinds of neuropsychological tests to programming games with Spry Learning. We have Peyton Bissell here with representing those days. It's a long history here. But the time has come for Zephy to discuss a completely new model of attention, divided attention in particular, and looking forward to this. As a heads up, we will give him about 45 minutes to present his work and allow the audience then to ask questions at the end. Then we will ask you to gracefully leave because the rest of the committee will grill him very severely. So, and we'll release him afterwards. What time is the class?
Yeah, I think we're going to go upstairs.
Okay, we'll have to adjourn to another. We'll all have to move out of here at 4 o'clock. Thank you for the heads up on that. So, yeah. Okay, we're ready to go. Thank you,
right.
Zephy.
Thank you, Holly. I am excited. That was a wonderful introduction. I've forgotten my entire talk. This is great. Lynn, go ahead. They can handle a little divided attention, I'm sure. So, as Holly mentioned, this is my dissertation work. It's been a long time coming. I'm super excited to talk to you about it. And it's on divided attention, particularly how we can understand that in its relation to aging and cognition through unobtrusive continuous measures. Just to start off, this is where we're going. These are the points that you ought to look at and say, wow, that's pretty cool. Or at least I look at them and say that. These are the major contributions of this work. The first is divided attention can be measured through measuring an interaction in a dual task test. Now, some of you who know what that is might think, oh yeah, that makes a lot of sense. And others of you might not know what that is. That's totally fine. We'll be going over it. But it's a pretty cool discovery. We've also enhanced one of the standard tests of divided attention by measuring an interaction. And the really cool stuff in terms of applying this to the world and specifically gerontology, allowing people to age in place, is that we can actually measure the same sort of thing through a cognitive computer game. But it's going to take us a little while to get there. So we do have a roadmap. First, a little overview and motivation, and then I'm going to be talking about the standard test that we use, which is the useful field of view test, or UFOV, the game that we use, which is called 21 Tally, and then how we enhanced these to sort of put them into the lab and actually do these tests, then the pilot study and the main study. In terms of motivation, all of you know this, but you might not know just how bad it is. Cognitive decline is incredibly expensive, both in terms of dollars and particularly in terms of time. You can read these for yourselves and be aghast as I am. I'm just going to emphasize this one down here. 15 million unpaid caregivers. That's friends, family, who are spending their time, which could be used elsewise in potentially, societally productive ways, to care for people with cognitive decline. And this is right now. This is pre of the 76 million baby boomers going into serious cognitive decline time. This is only going to go up a lot really soon. So we need to find some way to keep these people active, to keep them in their homes, to allow them to age in place. Otherwise, this is all our country is going to do. And that's pretty scary. One of the best ways that we can do this, I argue, is through unobtrusive continuous in-home monitoring. Now, before we get into what exactly that is and why it's better, let's talk about the way that people are tested for cognitive decline and Alzheimer's disease right now. Right now, you come into the lab and you go through a battery of neuropsychological tests and you get a diagnosis. You have Alzheimer's, you don't have Alzheimer's, you have mild cognitive impairment. Now, that's fine for diagnosing something like a broken leg. It's not very good for diagnosing something like cognitive decline, which, first of all, happens over a very long time, potentially starts when you're 20 years old and continues on. And it's really bad for something like cognitive decline, where one of the prime characteristics of it is that it gets more variable as you continue on. So when you go into the neuropsychologist's office, they have no idea whether you're having a good day, a bad day, or a standard day. You can't compare it to your own baseline because they have no idea what your baseline is. They don't know what your variability, your day-to-day variability is, your week-to-week variability. So they have no idea what your decline is. And when you're comparing to some sort of national standard, they don't know whether you started out as a genius or a mediocre level or less than that in terms of your cognitive abilities. So it's a bit of a problem. Now, if you were to have a measurement that was taken from your daily life or something that you liked to do on a daily or weekly basis, this would be more of a continuous measure, and that would allow you to measure these sorts of trends. And if this were unobtrusive, if this were something that you didn't have to go out of your way to do, that would be excellent. It would solve a lot of these problems. It would allow you to compare to your own baseline, take data from activities that are already happening, and get these trend data that are really important. In addition, potentially, you would not have to have a one-on-one, expensive, highly trained person looking at your data and no one else's data during that hour or 2 hours of your battery. So it may be cost-effective. However, this is not a silver bullet or anything like that. There are cons to this. These are noisy data. If you design a test to specifically talk about, for instance, divided attention, that test likely measures divided attention. Whereas if you were taking it from, for instance, a cognitive computer game, there might be other things going on. So it's noisy. There are initial setup costs because you go into a home. No home is exactly like any other home. And there are obviously privacy and security concerns. I'm not going to talk about any of that right now. Suffice it to say that I think this is the wave of the future in terms of monitoring cognition. And one of the best ways that I think we can monitor cognition in this unobtrusive continuous way is through cognitive computer games. Now, you may have seen this slide before. I've certainly talked about it a few times since we developed these games in 2006 or so. These games have been through many pilot tests and usability tests. And the one that I'm particularly going to be talking about now is this 21 tally game. And the reason that is that divided attention, which this game is designed to measure, is one of the first cognitive problems to decline when you start to cognitively decline. And that makes it a very important thing to measure if you're trying to catch when someone starts to cognitively decline. And it also is one of the major skills that you need to interact with our increasingly diverse and cell phones going off and everything happening at once environment. So it's an important skill that we need to keep as we age, and it's also a skill that unfortunately declines fairly quickly as we age. So what is attention? Very broadly, we could think of attention as something as a cognitive skill where you pay attention to relevant stimuli in pursuit of some goal. And often you have to ignore some distractors, right, in order to pursue this goal. Now, divided attention, same sort of thing, except that you have multiple stimuli that you need to pay attention to. And I love this definition that I got from Misha, which says, it's a skill which allows attention to multiple simultaneous stimuli required to achieve some goal. Perfect, right? And if you have heard about divided attention before, you've probably heard about it in the context of driving and texting and that sort of thing. And the reason why is that driving is already an intensely divided attention using skill. You have to pay attention to many things that are happening. You have to pay attention to the stoplights and the stop signs and other cars and who's merging, as well as the radio and the air conditioning and who's talking to you at the same time. So as soon as you are adding another device like text or food or something like that, then your attention is stretched much thinner. You are adding more division, and you may have some sort of a problem. So that's the context that many people have talked about in terms of divided attention. So this brings us to our research question, which is, can we accurately measure divided attention using some sort of naturalistic gameplay in a clinically meaningful way? Can we measure this using a game? Can we measure it at all using a test? That's what we're going to explore. In order to do that, we need to have some sort of a standard test of divided attention. And the test that correlates best with driving ability is the useful field of view test. And this is the standard useful field of view test, the second part of the useful field of view test. And in it, you have an icon, either a car or a truck, that appears in the center of your field of view. And you have another icon, a car, that appears somewhere on the periphery of your field of view. And these flash up for a fairly brief amount of time, something like that. Okay? That was pretty fast. Did you see it? Now that you're looking for it, you ought to be able to look at this and answer a couple of questions. There it is. And the questions are, what was in the center? Was it a car or a truck? And where was the thing on the periphery? So you get asked, was this a car or a truck? I don't remember now. I think it was a car. And where was it on the periphery? In one of these 8 locations. I think it was up in the upper right there. And that is the useful field of view test. And if you get these questions right, then the duration of the stimulus decreases. And if you get them wrong, the duration increases. So it goes in a staircase algorithm to find your 75% accuracy threshold duration. And you'll hear me refer to that over and over in this test. This is an important number, as the threshold duration, the 75% accuracy duration, that sort of thing. And the reason is that this is your score on the useful field of view, right? And so it goes shorter, longer, shorter, longer, shorter, longer, shorter, longer, until you get to approximately 75%. And then you stop and you get this score. That's your threshold score. Now, there are a couple of problems with this test. Some of them are problems with a test as a test, such as these icons are arbitrary. They're very close together. They're odd. They also happen to be proprietary. And this test is, in fact, commercial. It costs money to take, and that may be why they were created in this particular way. But there are also only 2 of them. And so when you're choosing in the center, even if you had your eyes closed for the entire duration, you got a 50% guess rate. That's just odd. Why would you make a test like that when you're trying to measure the difference in 2 different tasks? Divided attention, right? You're doing 2 things at once. Well, if one of them has a 50% guess rate, that seems strange. But I really want to focus on this last problem, which is the problem of this test as a test of divided attention. The only thing that you change in terms of changing the difficulty of these tasks is the duration of the stimulus. That means that both of the difficulties are changing at the same time. You're never changing one without changing the other. So you can't really tell what the difficulty of one task changing would do to your performance on the other task, which was really what you would want to know in terms of dividing your attention. All you really know in this task is, well, you do know something about divided attention. For instance, if I were taking this test and you were taking this test, and your ability to pay attention to two things at once was much better than mine, you probably would get a better score on this test than I would. However, it's conflated with this idea of speed of processing. Because what if my ability to take in this image and process it in my brain, code it as something, and spit it back out as some sort of a solution, I know where this was and what this was, is much faster than yours? Well, then I would do better on this test even if I weren't very good at doing two things at once. So it's measuring speed of processing as well as divided attention, and that's a problem because these are potentially quite different neurological processes. So we really want to separate those out. Which brings us to specific aim number 1, which is basically, can we separate those out? We would like to build some sort of a model of divided attention that differentiates divided attention from speed of processing, and particularly develop some sort of a test that specifically tests divided attention, because that's what we want to know about. We don't really want to know about speed of processing. So let's talk about what divided attention might look like in order to sort of visualize why we should be what we should be measuring and why we should be doing the tests that we do. So if you just imagine for a moment that your brain is a computer and it has some parallel processors like this, you throw in a problem and it spits out a solution. That's very nice. If you have some sort of an easy task, maybe you're only using a couple of these processors at once. It's no problem. And if you have a medium task, still you can handle it. It's not a problem. But if you have a hard task, maybe you're using up all your processors. So in order to deal with this task, you have a couple of choices. And it comes down to what we call the speed-accuracy trade-off. You can either cut off that solution before you're really done marinating on it, in which case your accuracy is going to go down, or you extend it a little bit. You take a little bit more time in order to deal with this problem, and then you have an accurate solution. And so that's going to show up in our threshold value. If we're keeping the accuracy the same, 75% accuracy, it's going to take you longer to get there, so your score is going to be longer. It turns out this applies in exactly the same way to divided attention. Doing two easy tasks, if you can handle it, no problem. As soon as you're doing two medium tasks, and especially two hard tasks, one task is going to start to interfere with the other a lot more. And that's what we're measuring. That's what we want to measure. And in terms of measuring this in the lab, if you were to think about, those of you who are of a mathematical bent, if you were to think about what would it look like to measure something where one task, the difficulty increasing here, is interfering with my performance on this other task, that's an interaction. So if we were to map, I should say, graph task 1 going from easy all the way up to hard here, and we were to keep the other task easy, maybe you're able to handle that. Maybe it gets a little bit, maybe your threshold value gets a little bit longer, but not particularly longer. But if you had an interaction, as you increase the difficulty of the other task, this slope is going to increase and increase. And that's what an interaction looks like. That's what we're trying to measure here. Okay? So that's our idea of divided attention. So how are we going to get there? Well, in terms of this test, say the useful field of view test, and you'll see it'll apply as well to this 21 tally game, we have two tasks, and we need to be able to accurately change the difficulty of both of those subtasks, right? The central subtask, where you're asking what is in the center, and the peripheral subtask, where you're asking where is this thing on the periphery. We need to be able to change those difficulty levels in such a way that we get a measurable response. So when it gets harder, your threshold value gets longer, and when it gets easier, your threshold value gets less easy. So in order to do this, we had a pilot study. This was a convenient sample of 10 people. There were a fairly large age range, and many of the people who took this are here, and I appreciate your help. Pardon me. And basically, they came into the lab, did the useful field of view, did the 21 tally experiment, and then we determined whether our attempted changes on each of these subtasks actually had a measurable effect on their threshold value. I want to tell you what we came up with. First of all, changes to the useful field of view. We got rid of these proprietary shapes for reasons we don't want to have any proprietary shapes in our new test, but also just so that we would have a normal, very recognizable shapes, just circles and crosses along the periphery. And then in the center, just English letters. And we had all English speakers, all English literate people, very recognizable. These letters are very recognizable. And we used these 8 specifically. Many people ask me why those 8 specifically. Well, we looked in the literature and found that these were not the least confusable, but an equal confusability with each other in this particular font of capital Helvetica. And I'll just show this. This is the confusability table. They were given many more than 100 times, but it's been normalized to 100. And you'll see each one was only confused with each other one less than 5 times, except for I, which was confused with P 7% of the time. So around the same amount of times. And we wanted to have 8 so that we would have a reasonable range of things that you couldn't just guess, right? Not just 2. But we also need to change the subtask effectively. Change the difficulty of the subtask, I should say. So the way we did that was on the periphery, rather than just having a luminance test like you have in the standard use of field of view. That is, all you have to do is see on the periphery something white, as opposed to all of the darkness. You actually have to have distractors in each of the other locations. So and equal luminance distractors, I should say. So the target is a circle with a cross in it, and the distractors are circles with X's in them, and you have to find the cross, right? So that's our peripheral task, and then we can change the difficulty simply by increasing or decreasing the number of distractors, which has a large literature that says that this will, in fact, change the difficulty, and it shows that our findings did show that as well, which is nice. And in the center, we also wanted to have a measurable thing that we could change in a particular way to have a measurable effect. So what we did was blur these letters, okay? So we could blur them by a certain number of pixels. I believe this is 0, 5, and 10 pixels of blur. After that, it gets really hard to tell what it is. And so that's how we changed the central task. So if you were to look at the absolute easiest of the sets of conditions for the subtasks to the very hardest, you'll notice there's no blur here, only 4 things on the periphery, 3 distractors and 1 target, versus a lot of blur and 11 distractors and 1 target on the periphery. This is a very hard task, as you can see. If that were to flash up 500 milliseconds, 600 milliseconds, you could do it, but it takes some practice and a lot of concentration. Whereas this one, it's pretty equivalent to the standard test. Flashes up, you can find it in 50 to 100 milliseconds without any trouble. Pardon me. But in order to have some sort of an application, I know this is the thing you've all been waiting for, and I've been waiting to tell you about it, we need to have some sort of a computer game equivalent to it. Something that someone will do, because people are not going to take this enhanced use of field of view test every day for the rest of their lives. Some of our elders said that they would, because they're very concerned about their cognition, but I don't want to do that. I would rather play computer games. So we want to translate this into something that people will do, either are doing now or will do. And the way that we did that is this 21 tally game. Now this can be thought of as blackjack in 2 dimensions. If you've ever played blackjack, you know that you're looking for 21 and you're trying not to go over 21. Anything under 21, you're fine. You're not good, you're not bad. But 21, you're golden. Over 21, that's considered a bust, and that's bad. And what you're trying to do in this game, you have 4x4 grid, 16 places to play this card, like so, and you're trying to get 21 in the rows or the columns at the same time. So if you were to play like so, I'll just play until we get to an interesting play that would have a 21. So here, so I can see if I were to play the 9 plus 12 in that row there, then I will get 21. So I'm going to put it here, but I ended up busting in the column. See? So this is the idea. If you are paying attention only to one dimension at a time, then you will not perform as well as someone who is paying attention to both dimensions at once. Hence the divided attention aspect of this game. Now, there are a couple of problems with this in terms of a lab setting. And basically, they are that this game was designed to be a game in someone's home over a long period of time, a year or 2 years, or it's in a 5-year study now. This is not intended to be in a lab setting where someone comes in for an hour or two and plays this game. The problem is that each of the divided attention intensive settings, boards, are relatively few and far between. You saw it took me 9 or 10 plays to get to something where I even potentially could have done a bust and a 21 at the same time. So what we need to do is redesign for the lab. Oh, and also I should mention one of our summer interns did some really excellent work saying that there are, as you might expect, different cognitive loads for different numbers of cards and open spaces on the board. So we need to equalize that out. We don't want to have that be part of our difficulty. Which brings us to specific game number 2, which is how can we make this game into something that we can clinically validate or have some sort of a predictive power in terms of measuring divided attention. And the way in which we did this is to make the 21 tally puzzle. And this is basically each board is no longer contiguous. You get one board, you get to play once on it, and then you get a completely new board. Okay? Each board has 8 open spaces and 8 cards. Each board has only one best place to play. Okay? So if you look at this one, your next card is the king. You can see that this is going to bust everywhere except in the bottom right. There's only one best place to play. And also, it gives us an ability to change the difficulty level on each of the 2 dimensions, which is important, right? Because we need to be able to do that in order to measure divided attention. So the way we change the difficulty level, is to say, on each of the 2 dimensions, how many different potential outcomes are there, right? In terms of bust, 21, or neither of those, right? So it could be anything from 1 to 3. And on this, you can see there are 2 in each one. In each one, you can either bust or not bust, right? And there's only one best place to play where you can not bust on both. The final thing that we did to make it more time pressure, much more like the useful field of view, is that we only allowed them to see the stimulus for a certain amount of time. And then the cards turn open. Okay? So you can still respond. You can still say, okay, this is where I should play, bottom right-hand corner. Or if you are not sure, then perhaps somewhere else, and then we know which one you got wrong. But you only get to see it for a certain amount of time, just like the useful field of view. So that's how we ended up dealing with the 21 tally, making it into more of a lab test. So let's talk about the main study. There are 2 things we're looking for here. First of all, is the interaction between these difficulties significant? Because if it is significant, then for that particular person, then we can measure their divided attention. Remember, the interaction is our proxy for a measure of divided attention. Because if you have a large interaction, then it's basically a measure of your inability to use your divided attention, right? If you have a large interaction, then your ability to use divided attention has been maxed out, and you can no longer deal with the difficulties of these 2 tasks at once. And if there is a significant interaction, then does the magnitude of that interaction translate? Does it equate between 21 tally and our enhanced useful field of view? Because if it does, then we're measuring the same thing. And if we're measuring the same thing and we're measuring divided attention, then we're golden. So let's talk about what we did. We brought 50 people in, huge age range. We tried to essentially get them into a roughly equivalent number of people in each age group, each category of age. Each person, we asked that they had played a computer game in the last year. This was basically as a screening purpose. We wanted people who had the familiarity with the computer and the mouse that they could actually take these tests. And also we wanted to be testing on people who would actually benefit from these procedures. If you're not ever going to play a computer game, then perhaps these tests, this work may not apply to you. This also was a convenience sample from around the Portland area, as you might expect. They're overwhelmingly white, very high education level. We did ask that people have no uncorrected vision problems. This meant something different to our elders than it meant to me. I meant that you would have vision corrected to 2020. And they said, I absolutely have a corrected vision. Not to 2020, though. So we had a few of our elders who had some vision problems, but we left them in because we love them all. So basically the protocol was very similar to the pilot study. We brought people in. We had them go through an instruction period which involved demos and practice on each of the tasks, the 21 tally and the use of field of view. And then they did the enhanced use of field of view, also did the standard use of field of view so we could get some sort of a comparison there, and one trial set of each of the sets of conditions for each of the tasks, the enhanced use of field of view and the 21 tally possible. So the sets of conditions, you'll remember, are the different difficulty levels of the subtasks. So for instance, one set of conditions would be easy central subtask and hard peripheral subtask. That would be one set of conditions. Now when we're trying to measure these things, what we really want to get at is the underlying internal neural processes. But we can't measure those directly. We don't have the IRB approval to measure those directly. So all we can measure is behavior, right? But this behavior is indicative of an internal neural process. And there are a couple processes that I want to focus on because we saw both of them, and I'll be talking about that. And one of them is a parallel process. This is what we talked about before with parallel processors, right? And this is, you're doing both of these things at the same time. And so the only thing that is affecting our measurement of your threshold value is whichever one takes longer. You're doing both of these at the same time. You stop doing the shorter one, for instance, in this case, the central task. You were done with that, but you're still working on the peripheral one. Well, the only thing that we can measure here is the peripheral one, because all we know is your sort of group threshold value. Now, if you contrast that with a serial process, this would be you're doing one task, you finish that task, and you do the other task. And in this case, there are both of the difficulty levels contribute to the overall threshold value, right? And there could be any number of mixed, from one to the other. But we're not going to talk about those because it would be very hard to sort of tease out where one stopped and the other one began. But we are going to talk about parallel and serial. And if you were talking about the mathematical representation of these, as you might expect, the parallel model is based on the maximum, whichever one takes longer. The serial model is an additive model. It's based on both of the threshold values. Okay? Now, what these look like in terms of our graph is fairly distinct. These two models look fairly distinct. So if you were to measure, again, one of the subtasks, in this case the central subtask, going from easy, medium, and hard, the easy peripheral value might be there, there, and there. So really, we're looking at a straight line because there's no increase in the difficulty, in the threshold measured based on increasing the central difficulty. There may be, in this case there is, an increase in the threshold as you increase the peripheral difficulty, right? So there's only one that's really affecting it. If you were to measure it the other way, with the peripheral difficulty down here, then you would see an increase in all three of these, right? These are the same data from the same person. This is toy data, of course. But the important part is, if you were to, for instance, take a one-way ANOVA of this easy peripheral, this easy task, keeping this task easy, this p-value would be greater than 0.05, and this p-value would be less than 0.05. What that means is there's no difference between these values, statistically speaking. And there is a statistical difference between these values because one of the tasks is, in fact, affecting the overall threshold value, and the other one isn't. Now, this is pretty interesting because we have actual data that looks exactly like that. So that's fun. One thing that you would need to know that these were the same, of course, the p-value tells you because it's greater than alpha of 0.05. But the box plots let you know that these median values are essentially no different statistically. And if you were to add the other values in, it gets a lot more complicated. this one also has no interaction. But the reason we don't focus on the hard values is because this could very well have an interaction, in which case this hard might go up to the sky, right? But this easy one stays equivalent with a p-value greater than 0.05. And if you map, again, this is the same data just mapped this way instead of this way, right? Then you can see all three of them just go up nicely like that. As the peripheral difficulty increases, their threshold value increases. So this is a person who is parallel processing, and the peripheral value, the peripheral task, subtask, is taking longer than the central subtask. Now I'd like to contrast that with the serial value, or the serial case. This is, again, a toy example. I don't really need to show it to you. But in each case, they increase because both of the tasks' difficulties are involved in the eventual threshold. And we also have data that that show this sort of an underlying process, a serial underlying process. So the p-values in both directions, I only have to show you one because they look quite similar, are less than 0.05, quite a bit less, in fact. So these are the median values are different. The other thing that we really want to focus on here is the interaction term, right? That's what we really want to get at. And it turns out that both of these processes both of these models, I should say, for almost everyone, fit better with an interaction term. And that's really great, because that means that we can actually compare your interaction term magnitude and say, okay, you have more of an interaction and therefore a worse divided attention than this person who has a smaller interaction and therefore a better divided attention. They're able to divide their attention and deal with both of these tasks at once. And some of these are really dramatic. This is not the same person I showed you before, but it's a person who also has no interaction. Really, you can see the bottom and the top fairly flat, right? Contrast with this, where the easy line down here is fairly flat, but the slope just increases dramatically as you talk about getting medium and then hard. This hard value, especially the hard value, their ability to deal with two hard tasks at once. Both of these tasks are interfering with the other one, causing this threshold value to just skyrocket. Excellent. Thanks. So I'm just going to switch gears here just for a moment and say that the other thing that you really want to look at in terms of a test like this is how does it measure up to the standard test? And I think this is really interesting. In order to do that, you're going to need a test-retest protocol, and luckily we did take the standard test a number of times so that we can give you. So you have a correlation value when you test-retest on the standard test of about 0.76, and that is in line with the literature. And if you compare the standard score to the enhanced UFOV easy, you have an equivalently high Pearson's R. Now, the interesting part about this is that the easy value represents the least amount of interference that we would have tested between one task and the other. Both of them are very easy, right? And that means it's the closest that we can get to measuring just your speed of processing. And this is our highest correlation with the standard test. Now that suggests that at least in this population, the standard test is really measuring speed of processing and not really measuring divided attention. And I'm going to skip over a few things here just to jump to this, which really puts that into perspective. You can see this is the enhanced UFOV, and all of these are correlations with the standard UFOV. And the easy is very high, and the hard is very low. So when you talk about having a large interference or measuring some sort of divided attention, your correlation with the standard test is very low. Now, I think that is interesting and should be looked into more. We haven't looked into it more, but it should be. And the grand finale, the thing that I think is really great, is the comparison between the magnitude of the interaction values in measuring 21 tally and the enhanced UFOV. We have a very high correlation value. Now, those of you who know how to calculate correlations are looking at this and saying, well, you do, but it's really because you have this one guy who's crazy out here. And that's true. But if you take him out, you still have about a 0.8. But that's not what I want to talk about. What I want to talk about is when you break it down by age group, it looks really like what you would expect, which is nice. The 75%, or rather the 75-plus people are higher than the rest. And pretty much everybody else is just down in this little clump down here. And if we were to zoom in, then you can see that, again, you have some 60s, 60-plus, some 50-plus, but pretty much everybody lower than 50 is down in this little clump right here. Now, although I will say, especially, there's this X right here, and if I zoom in again, I think you'll be able to see it. This guy is, I believe, 72 and doing just as well as any of the under 40s. And that's exactly what we would expect to see from the literature, and should be heartening, really, which is that as you age, your divided attention, your cognition may not decline, but your average as a group, your variability gets much bigger. So the group average gets much, much worse. And this really speaks to the problem that I was talking about before, because right now we're comparing all these neuropsychological tests to the group average. That's not appropriate for this guy at all, right? And so that's fun. It should look this way. It does look this way. I'm happy about that. You can be happy or not, but you should be. You should be happy. So we have a lot of cool data here. I've worked on it for a while. I think it deserves to be worked on for a while more. I'm excited about the future directions we could go with this. This deserves a longitudinal study. For some reason, they don't let grad students do a longitudinal study. And from where I'm standing right now, thank you. Because I would have jumped on it, and it would have been a mistake. The standard useful field of view, as I mentioned, was designed as a test of driving ability, right? An off-road driving test. So I would like to know how our test correlates with driving ability. I would love to have a simulated or even an on-road test to see, because if our easy is correlating with driving ability, is really correlating with driving ability, and our hard isn't, or for instance our interaction measure isn't, then that suggests that in terms of the driving tests that we have, what's really the most important is speed of processing and not divided attention. And that's interesting. I don't think that we have explored that, and certainly I don't have the data to explore it here, but I'd like to. The useful field of view test has been shown to be remediative in terms of bringing back your divided attention ability. I'd love to know if our tests or our games do that. And frankly, our current data, we have a lot more to look at that we simply didn't have time to look at. In conclusion, I believe you can measure, at least in this sample, divided attention by measuring the interaction and the magnitude of the interaction. That's pretty cool. And this enhanced useful field of view test can be used particularly to measure that divided attention in the absence of speed of processing, sort of to take those two differently and separate them out. And particularly, our 21 tally puzzle, which we hope would correlate to the 21 tally game that's out there, although we haven't done the work, can be used to measure the same thing that this enhanced useful field of view is measuring. So, a dissertation is not a singular activity, and I owe a massive debt of gratitude to my committee and everyone else, really. If your picture isn't up here, it should be. I thank you, and that's all I'm going to say. Thank you very much. And if you wouldn't mind, if you have a question, just push the button that says touch and hold it down. There will be a red light, and that will mean you're being recorded. Posterity. I answered them all. I'm sure they were paying attention. just hold it down there. Thanks.
All right. So the end goal, I guess, is to get these diagnostic tools into the houses so that people can continuously kind of track their own skill level with the divided attention.
Exactly.
And is it to see if they're declining over time? Is it to help them not decline over time? Like, what's the end goal?
It is, and I'm glad you asked that because I didn't have time to really get into it. But my mentor, Holly Jimison, has been working on a cognitive health coaching platform for a while now. And in terms of what can you do, everybody's declining. Some people are declining very slowly. So slowly it looks like they're not declining. But we're all declining. And if you can target what you're declining on, is your vocabulary suffering? Is your proprioception suffering? Is your divided attention suffering? Then, if those data are being taken from your everyday activities in the home and being uploaded to some sort of cognitive health coach, perhaps screened by some automated process, to deal with privacy issues or any other issues that you have, then that coach can say, "Hey, here are some tests. Here are some tasks that you might want to do to help with your issues in language, or it looks like you're having trouble with your sit-to-stand ability. Let's work on that today," or something like that. So that's the sort of platform that we're going for here, and that's the sort of thing that's going to keep people in their homes longer and be scalable, to a large population like we're looking at coming down the pike really soon here. So thanks. That's excellent point.
I think it's well known that humans typically keep track of like 3 to 7 objects. Have you looked at, I guess, how the number of objects you've sort of put in as distractors compares with performance?
Wow, that's an interesting question. Let me see if I can rephrase it to indicate my understanding. So there has been a lot of literature stating that we can remember somewhere between 3 and 8 things. I think that's right, yeah. And you're asking how that applies to the number of distractors on the periphery. Is that right? Okay, well, I hate to just say it doesn't. But really, we're talking about 2 different things here. So those sorts of tasks are really memory tasks. We're talking about, for instance, I'm going to read you off a list of things and see how can you recall them instantly? Can you recall them with a sort of a distractor interval, right? As opposed to this task, which is really either an instant perception task, right? Did you perceive it or not? That's all I want to know. Did you perceive it? Or a search task. And either one of those is sort of a different process in the brain. So I think the real interesting part that you got at, which is does the number of distractors on the periphery affect the eventual threshold value? And it turns out that it definitely does, and that's key to the whole experiment. So it's a good insight. But I don't think it really applies to the 3 to 8 that you were talking about. Karen, you had a question?
I did. So, in my very scientific book club, we read this book called The Middle-Aged Brain, I think is what it's called, and they describe in there different ways that people have trouble with divided attention. One of the things I was curious about, you did look at age categories. Was there anything unique about the middle-aged and older adults who did better?
Well, we haven't looked into that, but I would definitely like to. So, I mean, that's the instant answer, is that I don't know. But there were, considering the range that we saw in terms of our measurement of divided attention, which is the interaction, so a big range. And a lot of people do see a big range in terms of the oldest 75 plus, in terms of measuring their divided attention. And I don't know what has been discovered about their unique abilities. It wasn't really an in-depth qualitative set of surveys that we said. So I would really like to bring them in again and sort of find out what their lives have been like to investigate that. But right now we don't really know, other than to say, you're equivalent to a 40-year-old. Good job. Anyone else? Yes, Felicity.
I think mine might be a two-part but related question, so stick with me here. So the first one is you talked about the real-world application when Mike asked about this being part of a health coaching package. Does that mean that it stays sort of within the realm of, I go to the doctor when I'm 45 and they recommend that I get a health coach from then on? Do I get a health coach through the healthcare system, or is it like Sudoku, which they're selling like hotcakes because they're like, Sudoku keeps your brain smart? And related to that, what age do you start your baseline? I mean, we're always declining, pick your age, 25 or 30. What age do you start taking these tests so that you finally have a good baseline when you finally go south?
Well, that is an excellent two-part question. And the answer to both of them is, give me $20 a month and I will sign you up right now. But seriously, people are addressing all stages of this that you listed. There are lots of websites, as you mentioned, like Lumosity, something like that, where you can sign up and you can play things like Sudoku that will theoretically keep your brain sharp. And that's cool, but they don't have a lot of data behind them yet. And that's sort of what we're trying to do to sort of provide that. There are other tasks like Posit Science that will come into your community or your assisted living community and give you a series of tasks that are really intense but have been clinically shown to make a difference in your driving ability, your memory, or your I'm not sure they have a divided attention one. I haven't looked in a little while. But they're terrible. They're not games. They're not things that you would want to do. They're like, pay attention to the difference between these two tones. Boop, boop. Now, did the last one rise? Now imagine doing that for 2 hours a day for a month. It's really not fun, but it works. So we want to sort of bridge those two and bring them into something where someone can sign up. I would have to defer to Holly to say how it's going. There are a lot of daunting problems to say, partially this is definitely a medical intervention, so we would like to get some sort of trained professional and their compensation to be involved in that if you're going to have someone monitoring this. On the other hand, yes, I think you and I and everyone in this room would benefit from having our baselines taken now. And science would definitely benefit from that. So we could see, the moment that you started to decline, because, again, we still really don't know when you start to decline and when you start to decline faster versus someone else who is not declining faster. As you saw, a lot of the under 50s are really clumped up in terms of the global graph. Why are some of them moving faster than others? Looks like we got a class coming in. Crystal, I'll get you later. Liz?
Yeah. This is really about your testing, and as I understand it, it was mainly measuring rather than improving. My question is, many of us have taken the test. If we took it 10 more times, or you kept giving it to us every year or every 6 months, would we get better at it?
Right, and I'd like to know as well. Certainly there was a learning effect. I didn't go into it here. But from the first test that you took to the last test that you took, you got better overall at each individual test. But does that continue over a month or a year, and does it have any application to your actual divided attention ability? Those are the two things you would really want to know. And we don't know. Sign up for my next test. We'll figure it out. Thank you. Up to 513.